Okay guys, I was asked to give a solution to homework problem number 37. The problem statement is that we have a long solenoid with a diameter D. When a current exists, a uniform magnetic field is produced on the interior of the windings. By decreasing the current, the magnetic field changes by a rate of dB over dt, some rate of change. The question asks to calculate the magnitude of the induced electric field at two different distances. Okay, now obviously, your numbers on your particular problem will vary, but these are all the variables that are given. We're given the diameter D, so I'm going to say, remember our windings are here. If you'll recall, a solenoid looks something like this, like a slinky. The current goes through, right? It goes around and the magnetic field is produced on the interior. So if we're going to look down the center of the windings, that's what I'm going to draw here next. Right? If we're looking down the center of the windings, essentially what we have is, a magnetic field that way into the board, let's call it. Okay, there's our magnetic field, and this is everywhere inside the windings. Okay, there's our magnetic field into the board. Okay, all throughout. The diameter of the windings are given, right? So we know that the overall radius is going to be half the diameter. Okay, this is our radius, big R. Okay, and we're asked to find the magnitude of the electric field at various distances, or at two different distances. One, R1, is going to be inside the windings. It's some R1 here. And next, R2 is somewhere else out at a distance out here. There's R2, where R2 is larger than R, right? Than the radius of the windings, and R1 is less than R. Okay? All right, so the first thing we need to do is think about the fact that a changing magnetic field induces an electric field, right? We studied this in the lesson yesterday. We said that the line integral of a closed loop, the path integral E dot ds, was equal to the negative rate of change of magnetic flux. Okay, so there's our first sort of governing equation. All right, so for R1, when we're inside the windings, here's our path we're going to take. We're going to take some path, right, around the loop, right? We're going to take some path there, and we would evaluate the electric field at all points on that path via this part of our expression. So we're going to have the electric field, and the integral, the closed loop integral of our path, is just the length of that path. When I take a path that has some radius R1, what I get is the circumference of that path. That's 2 pi little r. Okay, so that's that side of the equation. We're going to evaluate over here the rate of change of flux. So we've got the negative. We've got the rate of change of flux. Remember that flux is B times the area times the cosine of the angle in between those two. In this case, I'm going to say that the area vector is in the same direction as the magnetic field vector, right? It's perpendicular to the windings itself, so this cosine goes to 1. The area that we're examining is not changing. It's the magnetic field that's changing. And the area that we're looking at is this area that's inside our path that we're examining, inside that loop of 2 pi r circumference. Okay, so I would write this as the electric field times 2 pi little r is equal to negative. The area of that is going to be the area of a circle, pi little r squared, and then the rate of change of magnetic field. Okay, at this point we can solve directly for the electric field, right? It just takes a little algebra. The pi's cancel. This one of these r's cancels with that, and we end up with the expression for the electric field as negative 1/2 r, that's little r, times the rate of change dB dt. And we're given little r, right? And we're given dB dt. So that's for part A, where R1 is less than big R. Okay, for part B, where R is greater than, R2 is greater than big R, right? We're out here. Let me erase this here. We have the same sort of situation. Path, or sorry, the magnetic field is still into the board, right? It's all in here, right? And we're looking for the electric field out at a distance of R2 from the center, right? So the governing equation is the same. We have the path length integral, right? The closed loop integral E dot ds is equal to negative the rate of change of flux, magnetic flux. The difference now is in our path, right? So the path in this case is out here, this circular path. So that's going to be the electric field times the whole path again. The length of that path is 2 pi little r. Again, in this case, little r is greater than the radius of our windings. Same over here, we got the negative of b dt of the flux, which is ba times the cosine of theta, or phi. That again goes to 1. Again, the area is not changing, it's the magnetic field that's changing. But what area do we have that contains magnetic field? Well, the area that contains magnetic field in this case is only the area that is bound by the windings itself. So our area is going to be pi big R squared times the rate of change of magnetic field. Okay, so when we're outside the windings, when we're looking at the electric field outside the winding, we end up with this expression, right? The pi's cancel, but the r's do not. So we get a negative 1/2 big R squared over little r times the rate of change of the magnetic field. Okay, now for both of these, they asked for the magnitude of that electric field, so we can, get rid of the negative sign. But essentially, that's what we've got for both inside the winding and outside the winding, calculating the electric field. All right? Thanks. Have a great day.